This is a combo section, sections 3.3 and 3.4, increasing and decreasing functions and the first derivative test, and the concavity and the second derivative test. So the primary concern of this combo section is to deduce facts about a function from information concerning its own derivatives. Okay, here's the first question. So if we have information on f prime, on the function f prime, what can we say about the function f? So if we have information about the derivative of a function, what can we say about the function itself? The following test, the increasing-decreasing test, answers this question. It says the following. If f prime is positive on an interval, so if you take the derivative of the function f at any point on a given interval, and you get always a positive entity, then the function f must be an increasing function on that interval. And if f prime is negative on an interval, meaning if you evaluate f prime at any point on that interval and you always get a negative entity, then the function f must be a decreasing function on that interval. Okay? Let's try to prove this theorem. Let's prove one of the two. Let's go with 1. 2 is very similar, okay? So proof of the increasing-decreasing test. And let's do just part 1 as we said, right? So what do we assume? We want to assume that f prime is positive on some interval, and we want to show it's increasing on that interval, right? Okay. So let's assume that f prime of x is positive for all x and some interval, let's call the interval I. Okay. And we want to show that f is increasing, meaning if we take two numbers a and b in that interval I, assuming that a and b are not the same and one is smaller than the other, so let's say a is smaller than b. Oops. We want to show that f of a is smaller than f of b, right? That's what it means, the function to be increasing on an interval I. Meaning if you take two numbers in I such that one is smaller than the other, their images are gonna behave the same way, right? The smaller input corresponds to the smaller output. That's what we want to show. Correct? So I want to just highlight what we want to show just to make it very clear. So this is what we want to show. Okay. And what do we have? We have that a and b are two numbers such that a is smaller than b. And where do a and b live? They live in I, the set I, right? Okay. Well, we were told that f prime is positive on an interval I, which means f prime exists on that interval, right? So f is differentiable on that set I, correct? On the interior of the set I. And those guys live inside I, so f prime exists. I mean, let me just show you on a picture what I mean. So I have a set, this is, let's say, I. This whole thing is I. And a and b live inside, so let's say a, and we said a is smaller than b, right? So if the function, if f is differentiable on all this purple set, it's certainly differentiable on this green set, because the green set is a subset there, right? Makes sense? So what I have is, I have that f is differentiable and hence continuous, right? Differentiability is a stronger notion. It's continuous on the closed and bounded set AB, and f is differentiable on the interior of the set AB, right? Correct? And by the intermediate value theorem, and not the intermediate, by the mean value theorem, what can we say? By the mean value theorem, we can say for sure that there exists some number C between A and B with the property that f of B minus f of A is equal to f prime of C times B minus A, right? This is what the mean value theorem tells us. Correct? All right. What do you know about f prime of C? Well, where does C live? C lives in AB, right? So C lives somewhere in AB. So in particular, it lives in I, right? It lives in the purple set I. And what do you know about f prime of any element that lives in I? Well, the derivative function acting at this number that comes from I is positive, and C is such a guy. So this is certainly a positive entity. Agree? Okay, so f prime of C is positive. B minus A, well, B is bigger than A, so B minus A is a positive number as well, right? So a positive number times a positive number is a positive number. So this whole product is positive, right? So the right-hand side of the equation is positive. As such, this whole thing must be positive, right? Agree with me? Because this guy is equal to a to this side, so, and this number is positive, so that difference must be positive. And what does this mean? And this means that f of A is smaller than f of B, right? As wanted to show. That's what we wanted to show, right? I mean, I just highlighted before. This is exactly what I wanted. Makes sense? So this shows part 1 of the increasing decreasing test, which says if f prime is positive on a set, then it must be increasing there. The second part is the same. I mean, I encourage you actually to do it. It's very much the same. All right, so now that we've showed it, we can use it at any moment we want, right? Let's try to employ that result, and let's employ it in example 1. Find where the function f of x equals 3x to the power 4 minus 4x cubed minus 12x squared plus 5 is an increasing function, and where it's the decreasing function. Okay, so find where this function is increasing and where it is decreasing. Okay, so this is example 1. We want to show where this function f of x which is 3x4 minus 4x cubed minus 12x squared plus 5 is increasing and where it is decreasing, right? Which means, according to the increasing and decreasing test just talked about above, to conclude that's, I mean, this is what I want to find, right? In order to find information about this, it suffices to find information about f prime. So let's find where f prime is positive and where f prime is negative, right? So we're going to make use of the increasing and decreasing test. As such, I need to find f prime, where it's positive and where it's negative. So let's find f prime. F prime of x is 12x cubed minus 12x squared, right, minus 24x plus 0, derivative of 5. And you can factor 12x, and you get the second degree polynomial, and the second degree polynomial is x squared minus x minus 2x, right? And this splits as x minus 2 times x plus 1, right? You can use quadratic formula if you wish, or many of you have the right intuition into it. Okay. All right. So I want to find where f prime is positive and where f prime is negative to find where f is increasing and where f is decreasing. All right. So you've learned the technique. This is a product, right? This is a product. You've learned the technique in college algebra. So you do it your way. I'm gonna do it a way I know. Okay. So I'm gonna create, if you were my student in college algebra, you know what I mean. I'm gonna create a table of variations. And here I have three factors: 12x, x minus 2, and x plus 1. Well, 12 is not contributing because 12 is positive, right? So technically the factors that are contributing to the sign of f prime are x, x minus 2, and x plus 1. So let me create the table of variations, which is the table of the variations of the factors, okay? And I have, as I said, three factors that are contributing to the sign of f prime. They are namely x, x minus 2, and x plus 1. Correct. The first row is the number line. This is where x live. All right, so x is 0. I mean, this factor becomes 0 if x is 0, right? This factor becomes 0 if x is 2. And this factor becomes 0 if x is negative 1. All right. So these are points that are important to the product. Okay. So let me just have a rest station at these points. So this factor is 0 at 0. So at 0, this factor is 0. Before that, it's preserving one sign. After that, it's preserving one sign. That sign is negative before and positive after. At 2, this factor is 0, which means before that it's preserving a sign, and after that it's preserving a sign, because that's the only time it neutralizes. It neutralizes, right? It happens before that. You can check. Take a point before 2, you get a negative entity. And if you take a number after 2, that number is going to be positive, right? The output. And for x plus 1, it's 0 at this point, and negative before, positive after. Okay. And now the last row is what I want. What do I want? I want the product, right? This is f prime. F prime, which is 12 times these guys, correct? 12 times these guys. But 12 is positive, so the sign of f prime, you know what? Let me include 12 in the first one. It's not going to change anything, right? So I'm counting this as one factor, 12x, and this is the sign of 12x is the same as the sign of x, right? So the first row doesn't change. Now this product is f prime, right? Okay. So I'm gonna now find information about f prime. I'm gonna have a row for that thing that I want to know about. And as we said, f prime is the product of all these, right? And between minus infinity and minus 1, this factor is negative, this factor is negative, and this factor is negative. So the product, which is f prime, is negative, because negative times negative times negative is negative, right? When x is between when x is -1, one of the factors is 0, then f prime, which is the product, is certainly 0. When x is between, again, the first row is for x, this is where x lives. When x is between -1 and 0, one of the factors is negative, another one is negative, and the third one is positive. So the product is negative times positive is positive. And at 0, when x reaches 0, one of the factors is 0, namely this guy, right? And hence the product is going to be 0. And between 0 and 2, two factors are positive, one factor is negative, so the product is negative. At 2, one factor is 0, so the product is 0. And after 2, everybody is positive, so the product is positive, right? Makes sense? So now, because of the increasing decreasing test, now I know where f is increasing and where f is decreasing. How about I create a row for f? So I'm setting the stage for a row for f. Let me change color. How about the pink here? Well, here f prime is decreasing between minus infinity and minus 1, right? Sorry, f prime is negative between minus infinity and -1, so f must be a decreasing function, right? I'm gonna denote decreasing by a decreasing arrow like this. How about that? So f is decreasing here. Between -1 and 0, the function starts f prime start being positive, so f is gonna increase based on the increasing decreasing test. Let me be very, very clear. The last row is because, so the information about the last row is by the increasing decreasing test, right? Correct? So this last row is because of the increasing decreasing test. So once you know information about the sign of f prime, you have you know exactly what f is doing. Is it increasing or decreasing, right? All right. So we are in the process of completing the row of f. Now between 0 and 2, f prime is negative. So f is going to be a decreasing function. And after that, f prime starts being positive. As such, the function is going to be an increasing function. Makes sense? So the behavior of f is decreasing from minus infinity to -1, increasing back from -1 to 0, decreasing again between 0 and 2, and between 2 and plus infinity, the function keeps increasing. So if you want to record that thing, so f, let me zoom out a little bit. So f is increasing on what is it? It's increasing here, -1 to 0. Union 2 plus infinity, right? And f is decreasing on over here, minus infinity to -1, union 0, 2, right? Okay. Let's continue the theory. All right, so we finished example 1. So let's read this paragraph here. Recall that if a function f has a local maximum or minimum at a number c, then this number c must be a critical number of the function. This is Fermat's theorem, if you remember from the previous section. Remember critical numbers? They are numbers, we had two types. Either they are numbers that are lost when you differentiate it, in the sense that those numbers live in the domain of the function, but do not live in the domain of the derivative of the function. And the other type is, at these points, the derivative function vanishes, right? So f prime of those numbers, at those numbers, is equal to 0. All right, but the other way around doesn't work, and we showed it in the previous section. If you have a critical number that doesn't force that at this number I'm going to have a maximum or a minimum, right? And the example we gave was x cubed. 0 is a critical number for x cubed because the derivative of x cubed vanishes at 0. But 0 is not is neither a maximum nor a minimum, right? Okay. So we therefore need a test that will tell us whether or not the function f has a local maximum or minimum at a critical number. So the question is, I'm trying to go back in Fermat's theorem, right? If I have a critical number, how do I know that at this number I'm going to have a maximum or minimum? What type of additional assumption I should have so that the backward direction of Fermat's theorem holds? Okay, this is the essence of the next test. So what's the next test? The first derivative test. Suppose that c is a critical number of a continuous function f. Okay, so suppose that c is a critical number of a continuous function f, near c, in a neighborhood of c. Okay, let's be more precise. All right, so around c the function f is continuous. Then if f prime changes from positive to negative at this point c, then the function is going to have a local minimum, a maximum at this point, right? So if the function f prime changes from positive to negative at this number c, then f is going to have a local maximum at c. If f prime changes from negative to positive at this critical number c, then f is going to have a local minimum at this number c. And finally, if f prime doesn't change sign at the number c, f is not going to have it's not going to have neither a local maximum nor a local minimum at this number c. Okay, I mean, this first derivative test is a consequence of the test we just talked about above, the increasing decreasing test. Okay, let me try to convince you via the last example we dealt with. Look at this function, f of x equals 3x4 minus 4x cubed minus 12x squared plus 5. Well, we found the only critical numbers we found here are minus 1, right? They are of the second type. They are minus 1, 2, and 0, correct? And according to what we found at the time, we found that f is decreasing all the way between minus infinity to negative 1, and it starts picking up again from minus 1 to 0, right? So at this number, minus 1, the function was decreasing and then it started picking up. It's not hard to believe that at this point, at negative 1, the function is going to have a local minimum, right? Because the function is going down and then up. And what does it mean in terms of f prime? It went from negative to positive. So it changed signs. This is exactly the first derivative test, right? If it changes sign, in this case it went negative to positive, right? It went negative to positive at negative 1, then the function is going to have a local minimum there. Okay? You agree with that? Now at 0, the function was increasing between -1 to 0, and at 0 it reach a maximum, right, and start decreasing back, correct? And what this means in terms of f prime changed from positive to negative. Makes sense? At this critical number 0, and so on and so forth. All right, so continuity obviously is embedded in the discussion. It's implicit here because the function is a polynomial. It's continuous everywhere, in particular around its critical numbers. Okay, so these are the additional assumptions that you have to consider in order to go back in Fermat's theorem. So if you have a critical number and the function is continuous around this number, and in addition to that f prime changes sign at this critical number, then you can go back and infer that at this number the function is going to have either local minimum or local maximum. Okay, right, let's go to the next example. Example 2. Find the local minimum and maximum values of the function f in example 1. So we talked about it. So at -1, since the function f prime changed sign from negative to positive, and hence the function f is changing from being decreasing to being increasing, then at this number f of -1, or at this number -1, the function is going to reach a minimum, a local minimum, right? So this is f of -1 here. F of -1 is the minimum point it's going to reach in that neighborhood, right? The neighborhood of -1. Just replace x by -1 in the function and get what f of -1 is, right? In the function, just replace x by -1 and find what f of -1 is. And when you do so, you should get a 0. Okay, you should get a 0 here. And for this guy, at 0, the function is reaching a local maximum, and at 0, the function's value is 5, right? So the function's value is 5 at 0. And then it decreases all the way to 2, and then starts increasing. So at 2, I'm going to have a local minimum, which is f of 2. And f of 2, if you evaluate the function at 2, you should get -27. Okay. So I'm having, at -1, I'm going to have a local minimum. So -1 comma 0, the value is 0. And at 2, I'm going to have a local minimum, and the value is -27. And at 0, I'm going to have a local maximum, right? Let me go to Desmos and try to show you how the graph looks like actually. Okay, this is the graph of the function we were dealing with. Look, at -1 comma 0, I have a local minimum as indicated before. At 0 comma 5, we have a local maximum, right? It's certainly a local one, it's not a global one because the function goes beyond 5. And at 2 comma -27, I have this local minimum, right? As we found before. Okay, and the function increases back. So the function increases back after that number, and it was decreasing initially and then start picking up again after 0, right? So all this information that you see on this picture we've already discovered before, right? In this table. All right, so this is example 2. Example 3, find the local maximum and minimum values of the function g of x equals x plus 2 sine x when x is between 0 and 2 pi. Okay, let's go to the next page and try to write the details of the solution of this example. So this is example 3. So the function is g of x equals x plus 2 sine x. And we are talking about x's being bounded below by 0 and bounded above by 2 pi, right? Okay, so in order to find local maximum and local minimum values, I want to find the critical numbers first, right? I'm trying to employ the first derivative test. This function g is continuous everywhere. I would like to find the critical numbers of g. They are since the function g is differentiable everywhere, then the only critical numbers are going to be those which allow g to vanish, right? G prime to vanish. So let's find where g prime vanishes. So we need to find g prime first, and g prime is 1 plus twice cosine x, right? And this is 0 if and only if cosine of x is minus half, correct? And you go back to trig class. Let me try to explain as much as possible here. So we have the unit circle, all right? This is a unit circle, let's say, and we want cosine to be negative half. Well, cosine is the first coordinate of the terminal point determined by x, and if you want this to be negative half, it means that you want this is the vertical line, negative half, right? So you want the terminal point to be either here or here. These are within one revolution. These are the only 2 points. These are the only two terminal points whose first coordinate is minus half, correct? And this point here corresponds to which angle? Well, this point here corresponds to this angle. And what is this angle? Well, what's the reference angle? The reference angle is pi over 3, right? The reference angle is pi over 3. So that angle is going to be pi minus pi over 3. So that angle is going to be pi minus pi over 3. And what's pi minus pi over 3? It's 2 pi over 3, correct? And the other point corresponds to this angle. And since the reference angle is pi over 3, and this is in quadrant 3, this blue angle is going to be pi plus pi over 3, right? So it's going to be pi plus pi over 3, and pi plus pi over 3 is 4 pi over 3, yes? 4 pi over 3. So these are the only 2 points within one revolution, or these are the only 2 angles within one revolution that allow you to say that cosine of that angle is going to be negative half. All right. So this happens if and only if x is either 2 pi over 3 or x is equal to 4 pi over 3. Right? All right. As we said, g prime, where g prime vanishes, is going to give us the critical numbers. And these are the only critical numbers for g because the function g is differentiable everywhere. So the second type that gives us critical numbers, in some sense, this type is empty. That type is empty, right? There's no point where g exists and g prime doesn't exist, correct? All right, so what do we get? So now I know that these numbers are critical. I want to know now where g prime is positive and where it's negative, right? Why? Because I want to see where it changes sign. By the first derivative test, I get my hands on the local extrema, correct? All right, so let's see where the function changes sign. Well, the function g prime vanishes at those points, right? G prime vanishes at those points, which means at these points, and these are the only points where g prime vanishes in 0 to pi. Which means before that is going to preserve one sign, and after that is going to preserve one sign, correct? How about we create a mini table of variations here? How about we drop these bars that we were talking about before? I know that at these points f prime is 0, right? We talked about that before. Or g prime in this case, sorry. So g prime is 0 at those points. Before that and all the way to 0, right? All the way to 0. So the lower bound is 0 and the upper bound is 2 pi, right? This is what we know. So at 0, between 0 and this number, the function is going to preserve one sign. Take a number between 0 and 2 pi over 3 and check g prime there. How about pi over 2? How about you evaluate g prime at pi over 2? Well, plug in pi over 2 and g prime. Again, I'm evaluating g prime. I'm trying to see the variations of g prime. We chose a number here. We know the function between 0 and 2 pi over 3 is going to preserve one sign, right? Why? Because if it were to change a sign between 0 and 2 pi over 3, then it should have been 0 somewhere in between, correct? What does it mean for g prime to change sign? It goes like from plus to minus or minus to plus. It means somewhere it neutralized. And we know that this is the first time it neutralizes after 0. As such, there's no way it's gonna change sign in between, right? This is the essence of the discussion. All right, so that means the sign is unique here. That's why I'm gonna take any point between 0 and 2 pi over 3 and test g prime there and see what the sign, and then the sign I'm gonna put it here. We chose pi over 2, which is between 0 and 2 pi over 3. Well, what's g prime of pi over 2? Plug in pi over 2 here. You get cosine of pi over 2 is 0. 2 times 0 is 0. 1 plus 0 is 1. So the sign is plus. Now between 2 pi over 3, right, and 4 pi over 3. So at 2 pi over 3, g prime is 0. We know that. At 4 pi over 3, the function is 0. G prime, the function g prime is 0. So in between, it doesn't neutralize in between. This means the sign is unique, either positive or negative. So how do we know? Take a number between 2 pi over 3 and 4 pi over 3 and test g prime there. A nice number would be pi, let's say. You can take any number between 2 pi over 3 and 4 pi over 3. Any number, any angle between 2 pi over 3 and 4 pi over 3. I'm taking pi. For pi, g prime of pi is 1 plus 2 cosine of pi. Cosine of pi is negative 1. 2 times negative 1 is negative 2. 1 minus 2 is negative 1. So the sign is negative here. Right? And between 4 pi over 3 and 2 pi, take a number between 4 pi over 3 and 2 pi. Again, the sign is going to be preserved. How about 3 pi over 2, right? How about 3 pi over 2? g prime of 3 pi over 2 is 1 plus 2 cosine of 3 pi over 2. Cosine of 3 pi over 2 is 0. 2 times 0 is 0. So that's going to be 1. And 1 has a positive sign, right? So g prime is positive between 0 and 2 pi over 3. G prime is negative between 2 pi over 3 and 4 pi over 3. And G prime is positive between 4 pi over 3 and 2 pi. What does this tell you about G by the increasing decreasing test? This tells you that G, let me just create a row for it. That tells you that G here is going to be increasing, right? G prime being positive, G is going to be increasing. And then here, since G prime is decreasing, that's going to be, since G prime is negative, that's going to be decreasing. G is going to be decreasing. And then since G prime here is positive between 4 pi over 3 and 2 pi, the function G is going to be increasing, right? Correct? So at 2 pi over 3, I'm going to have, by the first derivative test, at 2 pi over 3, G prime changes from positive to negative. By the first derivative test, let's go back to this, where is it? By the first derivative test, since the function changes from positive to negative at 2 pi over 3, then the function is going to have a local maximum at this number. Correct? Oops. Over here. Correct? So at 2 pi over 3, I'm going to have a local maximum. And at 4 pi over 3, the function G prime changes from negative to positive. So at this number, I'm going to have a local minimum, right? All right, so what are these numbers? Let's find the local maximum value here. That's going to be G of 2 pi over 3, right? G of 2 pi over 3. And if you find go to the recipe of G and plug in 2 pi over 3 there, you're going to get, this number is going to be 2 pi over 3 plus square root of 3. Okay. So that's going to be G of 2 pi over 3. And at 4 pi over 3, the function is going to have a local minimum, and that number is going to be, if you compute it, 4 pi over 3 minus square root of 3. Okay. Which is a local minimum value for G. All right. So this is example 3. Let's go back. All right, so we've just finished example 3. The next question is, if we have information about the second derivative of a function, what can we deduce about the function itself? All right, so this is the next question. In order to be able to answer it, let me just get a terminology out of the way. Let's read this definition. If the graph of a function f lies above all of its tangents on an interval I, then it's called concave upward on I. Look at this graph here, the left graph. This graph corresponds to some function which is increasing. It can increase this way, and it can decrease, as in the right picture, this way, right? If it increases this way, its tangent at any point is going to be below the graph of the function, right? Such a graph is called concave upward on this interval, the first coordinate of A, first coordinate of B, whatever this interval is. And it's called concave downward as the other way happens. If the function actually is below all of its tangents on this interval, right? This is the concave downward thing. All right. So even though both of these functions are increasing in between the first coordinates of A and B, they can, I mean, one is increasing in a way where the bending is different, right? Where, I mean, the left graph sits on its tangents, whereas on this graph, the right one, the tangents in some sense sit on the graph, right? So this is a concave upward direction and this is a concave downward direction. Why this is important about f double prime in terms of knowing something about f double prime and translating knowledge to f? Well, take a look at this left graph. What can you say about the tangents? The tangents, which means f prime, right? F prime at this point, right, which means the slope of this tangent, is certainly smaller than the slope of this tangent, right? So f prime at this point is smaller than f prime at this point, and f prime at this point is smaller than f prime at this point. So we realize that the tangents are increasing. The slope of the tangents, I should say, are increasing, which means f prime is increasing here, correct? Which means f prime is increasing here. Whereas here, the tangent at this point, the slope is bigger than the slope of this tangent line, right? And this one is, what they say, I meant bigger, right? The slope of this tangent is bigger than the slope of this tangent. And the slope of this tangent in turn is bigger than the slope of this tangent. And this one is bigger than the slope of this tangent, right? So here the slope of the tangent is decreasing, correct? They're both positive, but the slopes here are increasing, the slopes here are decreasing. Make sense? So that should tell me that the derivative of the function f prime, because f prime is increasing here, f prime, right? The slopes are increasing here, so f prime is increasing here. Then somehow, by the increasing-decreasing test, I'm gonna be able to say that the derivative of f prime is gonna be positive, right? I mean, I have f prime being increasing, right? If somehow I'm saying from the increasing-decreasing test, if you know that the function is increasing, and by the function here I mean f prime, then its derivative is gonna be somehow positive, right? And what's the derivative of f prime? It's the second derivative, all right? And similarly here I have that the derivative is, so g prime here is decreasing, correct? Because the tangents are decreasing. Then somehow by the increasing-decreasing test, I'm gonna infer that the derivative of g prime is gonna be negative. And the derivative of g prime is g double prime, correct? So this discussion is written here. And let's record that observation. It's called the concavity test. And it reads as follows. By the way, if you'd like to see a proof of this, I'll be happy to do it, but you have to contact me in order to let me know that you care about the proof, and I'll record a video and give it to you. So here are the details that we just discussed. If the second derivative of a function is positive on an interval, then the graph is gonna be, the graph of the function is gonna concave upward. Okay, so the tangents are gonna be below the graph, right? So because in this case, this is the left figure, right? This is the left figure. So because the derivatives are increasing, so I'm expecting the derivative of that derivative to be positive, right? And then if If f double prime is negative on an interval I, then the graph of the function is going to be concave downward. Okay, so let's look at this example. Example 4, sketch a possible graph, so there are many answers here, of a function f that satisfies the following conditions. The function f prime has to be positive on minus infinity all the way to 1, and f prime has to be negative on 1 to infinity. So what can you say here? If f prime is positive on an interval, what can be said by the increasing-decreasing test? The function has to be increasing, right? The function f has to be increasing from minus infinity to 1. And f prime being negative on this interval, by the increasing-decreasing test, you know that the function f has to be decreasing on this interval, right? 1 to infinity. The second part, f double prime is positive on this interval and on this interval. Well, by the concavity test, you can say, because of this, you can say that the function is going to concave upward on both of these intervals, right? And the second part, the second condition in this in part 2 is by the concavity test is going to tell me that the function is going to concave downward on this interval. And lastly, as x goes to minus infinity, the values of the function approach -2, and as x goes to plus infinity, the values of the function approach 0, right? So this means at minus infinity, the function has y equals -2 as a horizontal asymptote, correct? Remember that. And as x approaches infinity, the function is approaching its horizontal asymptote y equals 0. So you want to graph a function that verifies all three. I gave you an example here, and I hope you come up with your own one. Okay. So observe that the function here is increasing from minus infinity all the way to 1. But from minus infinity to -2, it's going to concave upward. So it's concaving upward. And then from between -2 and 1, I'm still in the increasing part, -2, 1, it's concaving downward. It's going to keep concaving downward, but now from 1 to infinity, it's going to decrease, right? It's going to decrease while concaving downward all the way to 2. And then after 2, it's going to start being, it's going to keep decreasing, but it's going to start concaving upward, right? So it's going to sit above its tangent after 2. It's sitting below its tangents between -2 and 2, right? It's concaving downward. And as you see, y equals -2 is a horizontal asymptote at minus infinity, and at plus infinity, the x-axis is, or y equals 0 is horizontal asymptote. Okay. All right. Next definition. Points where the function changes concavity are called inflection points. Okay. So let's read the formal definition. A point P on a curve y equals f of x is called an inflection point if f is continuous. It has to be continuous there, and the curve must change concavity at this point, either from concave upward to concave downward, or from concave downward to concave upward at this point. Okay, so it has to be continuous in addition to change concavity. Right. Okay, so here's another application of the second derivative. Is the following test to get the maximum or minimum values of a function. It's a consequence of the concavity test. So I want you to think about this as a partial converse of the Fermat's theorem. Remember, Fermat's theorem was about the following. If you know that the function has a local maximum or local minimum at a number, then that number must be a critical number, right? And there are two types of critical numbers, as we discussed before. The first derivative test at the time, under additional assumptions, we can go back in Fermat, right? We can let the converse of Fermat hold. And what were the additional assumptions in the first derivative test? We wanted that this number, the critical number, to we want the function to be continuous in the neighborhood of that number, right? And we want the function f prime to change its sign, correct? So if f prime changes sign, if the derivative function changes sign, then the function itself is gonna be is gonna attain a local extremum at that critical number c, correct? Over here, it's still the same type of conclusions but different assumptions. You're still talking about critical number, but not of the first type, it's of the second type. Okay, critical number that allows the function f prime to vanish. And you're going to assume that f prime is continuous in a neighborhood of that critical number c. And you want to assume that f double prime at this number c, either positive or negative. If it's positive, then the function is going to attain a local minimum at this number c. And if f double prime at c is negative, then it's going to attain a local maximum at c. Okay, so this is why I said partial converse of the Fermat's theorem, because it's not for any critical point, it's for critical points that annihilate the derivative function, right? All right, so one more time, let's read this. If you have the function f double prime continuous in the neighborhood of the number c, and at c f prime vanishes, then if f double prime at c is positive, then the function is going to attain a local minimum at this number c. And if f double prime of c is negative, then the function is going to attain a local maximum there. Okay. Let me try to convince you orally why that's the case. Look, if f double prime of c is positive, let's talk about part one. If f double prime of c is positive, right, and f double prime is continuous near c, what does it mean that this function f double prime is continuous near c? In some sense, it means it doesn't change abruptly, right? Doesn't change its values in a very unexpected way. Right? So since f double prime at this point is positive and f double prime is continuous there, so it must be positive for a little while, right? That's what it means to be continuous there. So since f double prime of c is positive and f double prime is continuous around c, this means it has to be positive, and for a little while, right? In some small neighborhood of c. So around c, f double prime is going to remain positive, right? And so around c, f double prime is going to be positive. What does it mean by the concavity test? It means in that small neighborhood, the function is going to be concaving upward, which means it's going to sit above its tangents, right? So you're going to have this scenario. In a small neighborhood, the function is going to concave upward, right? It's going to concave upward, and what? And f prime of c is 0. And f prime of c, so this is c, let's say. F prime of c is 0, so you have a tangent here, horizontal tangent here. So this means that the function is attaining a minimum at this point, right? I'm just trying to give you a little insight into the proof, okay? All right. Let's take this example. Discuss the curve y equals x4 minus 4x cubed with respect to concavity, points of inflection, local maxima and minimum, and use this information to sketch the curve. Okay. All right, let me zoom in a little more. So we have this function, let's call it f of x. Let's call it f of x. Okay. And we want to study all of these and ultimately try to sketch the curve of the function. Well, what's f prime of x? Well, f prime of x is 4x cubed minus 12x squared, right? And if you want to factor 4x squared, you get x minus 3, right? So let's see where f prime is positive, where it's negative. I'm trying to see to deduce something about f using the increasing decreasing test. So the numbers that make f prime 0 are 0 and 3, right? So 0 and 3 are the critical numbers. And they are the only critical numbers because the function f is differentiable everywhere, right? The function f is differentiable everywhere. So these are the only critical numbers. So I have 0 and 3, the only critical numbers I have. So let's create the table of variations. So the function f prime, let me move a little more. So the function f prime at this point 0 is 0, at this point 3 is 0, right? F prime. And if you take a look at f prime, this term is non-negative, so x minus 3 is the factor that leads the sign of the entire thing, right? And it's x minus 3 is 0 at 3, and before 3 this is negative, so f prime is negative before that, and after 3 this is a positive entity, right? F prime is positive there, correct? So if x is between minus infinity and 0, the function f prime is negative. Between 0 and 3, the function f prime is negative. Between 3 and plus infinity, sorry about that, I'm pressing this by mistake. So plus infinity, the function f prime is positive, right? And how does this, what does it tell me about the function f? What does it tell me about the function f by the increasing decreasing test? Well, this tells me that f is decreasing between minus infinity and 0. Between 0 and 3 is also decreasing, and then it's increasing from 3 onward, right? Correct? So the first derivative test tells me that at 3 I have a local minimum. Am I correct? Because the function decreases and then starts being increasing. So here I have a local minimum, right? So let me write that. So I'm gonna have local minimum value at 3. So and that value is f of 3, right? And if you do f of 3, if you try to find f of 3, this is 3 to the power 4 minus 4 times 3 to the power 3, and that's going to be negative 27. Okay. At this point 0, sure, 0 is a critical number for f, but I'm not going to have a local extremum here, right? The function decreases and then keeps decreasing. So the function here is behaving like x cubed in some sense, right? The function is crossing its horizontal tangent. Make sense? So this number is what? F of 0. What's f of 0? F at 0, what is it? It's 0, right? So this is 0 as well. And this is neither a maximum nor a minimum. Okay. Also, if you wanna apply the second derivative test, you can apply it for 3, right? You can apply it for c equals 3. Why? Well, f double prime, I mean, what's f double prime? If you find the derivative of f prime, oh, how about we find it? Let's find f double prime. F double prime of x is equal to 12x squared minus 24x, right? And if you factor out 12x, you get x minus 2. Okay, so f double prime is continuous everywhere, right? Everywhere, let alone around 3, right? And f prime of 3 is 0. F prime of 3 is 0. What's f prime of f double prime of 3? F double prime of 3, plug in 3 here. This is gonna be 12 times 3, so positive, and 3 minus 2 positive. So it's gonna be positive. F double prime of 3 is positive, right? So we are in part 1. Then you're gonna have a local minimum at 3. Makes sense? So the second derivative applies for 3 and gives us the same result that the first derivative gave us. Okay, but at 0, this second derivative test doesn't apply, right? Why? Because I don't have at 0, I don't have f double prime positive nor negative. I have it 0. Check. F double prime at 0, this is 0, right? So I have neither this nor that, so as such the second derivative is gonna give us nothing, no information. All right, so the only way I'm gonna understand if at 0 an extremum is gonna occur is by appealing to the first derivative test, which we just did before, and we understood that at 0 there's nothing going on, right? The function, I mean, there is something going on, but I don't have an extremum there. The function is crossing that horizontal tangent at 0, 0. Makes sense? Okay. Let's try to find the concavity and the point of inflections of this. So we know now the extrema, the local extrema. Here they are. Actually, here it is, I should say. The only local minimum I have, or local extremum, is a minimum, and that thing happens at 3, and the value is negative 27. How about concavity and points of inflection? Concavity, points of inflection. For concavity, I'm going to run the concavity test, right? Where is it? This one. So I'm going to see where f double prime is positive, where f double prime is negative, and conclude whether f is going to be concave upward or downward. And for the inflection point, I'm going to see where the function f double prime is going to change sign, right? And I need the function to be continuous there, but the function f is continuous everywhere in this case because it's a polynomial. Correct? So we're going to go to f double prime, see where it's positive, where it's negative, and where it changes sign is gonna it's gonna give me the inflection points. All right, so let's see where this is positive, where it's negative. So f double prime of x is positive if and only if x is what? I mean, this is a product. If you want to do it this way, if you want to stick with the same approach, the table of variation, let's do so. So this is the table of variations for f double prime, right? So for f double prime, so f double prime, it has how many points annihilate f double prime? There are two, 0 and 2, right? So 0 and 2, correct? F double prime is 0 here and here. Makes sense? We want to see the sign of F double prime. If you don't see it, I mean, if you see it, great. If you don't see it, we're going to build the table of variations that we used to do before. All right. I mean, anyway, so you can do it. The result is going to be positive here, negative here, and positive here. Okay. So let me know if you need more explanation. Check where F double prime is positive. You're gonna do the same thing as we did above for table of variations. And by above, I mean this, right? No, not this one. I mean this one, right? So F double prime is the last row. So you're gonna take the factors here and see the variations of each factor and deduce the variations of F double prime. Okay. So at the end of the day, you're gonna get this as the last row for F double prime. And then what type of information you can get on for F here or on F here? Well, the concavity test tells you that since F double prime is positive, F is concaving upward. Let's abbreviate this by, or use acronyms here. CU for concaving upward. F double prime being negative, the function is going to, the graph is going to concave downward. And F double prime being positive, so the graph of the function is concaving upward, right? All right. And now from here to here, the function f is continuous. It's continuous everywhere. So the function f double prime is changing sign, right? F double prime is changing sign. Let me take you back to the inflection point definition. So the function has to be continuous and the curve changes concavity. What does it mean, changes concavity? It means, but the concavity test, it means that f double prime changes sign, right? So f is changing concavity here at 0. It's continuous at 0, so this is going to be an inflection point. So that's going to be an inflection point here. And similarly at 2, the function changes concavity from downward to upward. And this happens because f double prime changes signs. So that's going to be also an inflection point, right? So what's the inflection point here? 0, 0, right? And what's the inflection point here? 2 comma f of 2. And what's f of 2? 2 to power 4 minus 4 times 2 to power 3. And that thing is negative 16. Makes sense? All right, so now I have information about the concavity, points of inflection, local extrema, local minima. And now I'm ready to use this information to sketch the graph, the curve of the function f, right? So let's do that. So this is the y-axis. Actually, let me just take this a little more up. Okay, so this is the x-axis here. This is the y-axis. And what do we have? We have that f is decreasing from minus infinity to 0, 0. So 0, 0. And at 0, 0, at this point, I'm going to have a horizontal tangent, right? So let me denote this by in red. So I'm going to have a horizontal tangent here. How about this? Right? At 0, 0, so when x is 0, f prime is 0. So this means I'm going to have a horizontal tangent here. And at 3 as well. At 3, f prime is going to be 0. So at 3 comma negative 27, so 3 comma negative 27, let's say it's somewhere here. So this point is 3 comma negative 27. So I'm gonna have a horizontal tangent here as well, right? And I know that I mean, at this point, I'm gonna have a local minimum, right? Okay. And what are the inflection points? They are 0, 0. So this is an inflection point that's denoted in green. And 2, negative 16, so probably somewhere here, that's an inflection point. Right? So this point here is 2, negative 16. All right, the function f is decreasing from minus infinity to 0 while it's concaving upward, right? While it's concaving upward. One more time. I'm putting the information together. I'm letting them talk to one another here. F is decreasing, you see, is decreasing between minus infinity to 0. But between minus infinity to 0, the function is concaving upward. So it's going to decrease while being above its horizontal, while it being above its tangents, right? It's concaving upward. So something like that, right? It's decreasing while the graph being concave upward. Here, the function is going to attain its inflection point. It's going to change concavity. It's going to start concaving downward. And between 0 and 3, the function is going to decrease. So between 0 and 3, so let's say this is 3 here, right? So between 0 and 3, the function remains decreasing, so it's going to keep decreasing from here all the way to here. It's going to decrease, but I have to respect the concavity, right? While it's going to decrease between 0 and 3, it's going to concave downward between 0 and 2. So between 0 and 2, it's going to concave downward. So something like this. All right. And then, okay, this is not a great one. Let me try again. One more time. Let me promise you. Last time. All right, let me just keep it like this. And then between 2 and 3, it's going to, right, between 2 and 3, 2 is somewhere here. Between 2 and 3 is going to keep decreasing, but it's going to start concaving upward. So it's going to keep decreasing, but it's going to start concaving upward. And then from 3 onward, the function is increasing. So the function is going to increase, but while being concaving upward. So something like this, right? This is not a line, this is a curve, right? So while being like this. If you wanna see the exact one, let's go to Desmos and let's graph it. All right, this is the graph. You see, it's decreasing all the way to 0 while being concave upward. That's what we have, right? Something like this. And then between 0 and 2, it's gonna decrease while being concaving downward. 0 and 2. Okay, let's just zoom out here, actually. How about zooming in and just dragging it? So at 2, we're talking about this point, negative 16 here, right? 2 comma negative 16, this point. It's changing concavity here. It's changing concavity from concaving downward to concaving upward, right? And then from this point on, it's gonna start being concaving upward, but it's gonna keep decreasing all the way to this point, which is 3 comma negative 27, which we found, right? And then keeps increasing from this point on while being concaving upward, right? So something like this. All right. So this is how you collect information about f. So you collect information about f prime and translate what it means in terms of f, and collect information on f double prime and translate information to f. All right, so the last note here reads as follows. The second derivative test is inconclusive when f double prime of c is 0. We ran into this problem here, right? f double prime at 0 is 0, right? So as we said, since this happens, none of these two conditions is verified in the second derivative test, and as such, the second derivative test doesn't apply. It doesn't give us any information. In other words, at such a point, there might be a maximum, there might be a minimum, or there might be neither, as in the previous exercise, example 5. This test also fails when f double prime doesn't exist, right? Let's see. So as long as neither this nor that happens, the test is not applicable, right? It's not going to give me any information. So this is another scenario when f double prime doesn't exist. In both cases, the first derivative test has to be used, as we used here, right? To infer that at 0, 0, there's nothing going on besides just the function passing through its horizontal tangent. That's it. All right. In fact, this last comment here, in fact, even when both of them are applicable, the first and the second derivative test, the first is often easier to be used. Okay, so we use it more often than not. Okay. All right. Example 6, which I'm gonna leave as an exercise. So this is left as an exercise. Sketch the graph of the function f of x equals this. Okay. So if you run into any problem here, please contact me and I'll be happy to provide you with a solution. Okay. All right. So this is the end of this section, or this combo section.